Now that we started testing the capacitor a bit, I want to figure out how we control how quickly it charges and discharges. So Ep12 provided some information that helped me get started, and pretty much the equation seems to be pretty easy. We have our time, and that's equal to the resistance times the capacitance, and this is for an RC circuit. In other words, when we have a resistor and a capacitor in series. So I guess the capacitor could be first or the resistor could be first, but the point is that they're in series on a circuit. So we might have our power and our ground, and the current must flow between these two before it gets to ground. So if time equals R times C, then it seems pretty simple. Let's say we use a 1000 ohm resistor, so that's 1000 ohms. So we replace the R with 1000. And the capacitance, the one that we're using right now, is a 470 microfarad capacitor. So 470. It's expecting farads, which I assume that's how you spell it. And we only have microfarad, so we need to convert that. So we know that a microfarad is equal to 1000 millifarads, and 1 farad, of course, is equal to 1000 millifarads. What did I just say? Sorry. 1 millifarad is equal to 1000 microfarads. So if we have 470 microfarads, it's equal to 0.470 millifarads, and then we divide it by 1000 again, so 1, 2, 3, we get 0.00047 farads. So if we plug this in, right, we're just converting 470 microfarad to regular farads, then we get our resistance, which is 1000, and we multiply it by 0.00047. So we multiply it, we just basically are moving our decimal back to where it was. So we get 0.47 seconds is T. And what Jay Beckville was saying is that 5 of these, and I looked it up afterwards, of course, basically 5 of these is how long a capacitor takes to charge. So we multiply by 5, and we get roughly 2.5 seconds. So I guess the charging time equals 2.5 seconds, roughly. I have this oscilloscope here where we can hopefully monitor the voltage as it moves. 2.5 seconds is a little bit quick. Maybe what we can do is add another 1000 ohm resistor, so we can double this. So instead of having 1000, we can have 2000, and this will be roughly equal to 5 seconds. Maybe that's better. So I'll put 2 resistors in series and try it out. So let's see if this works. So I have my breadboard, I have my capacitor. If you didn't see in the last video, the way to discharge them when you're done, at least what I've been using, is putting in a resistor and then just shorting it on the resistor. So I'm going to make sure it's at 0 volts. So we are at 0, perfect. All right, and then so now let's put our resistors in series. So we have 2 1000 ohm resistors, and I'm going to just attach one of them to VCC. I'm going to add the next one in series, and then the capacitor itself will just go from this second resistor to the ground. And I think this works. So I have my power over here that I need to connect, and then we need to find a way to get everything on screen. Okay, so this is not blocked too much by the light. I found out that I could turn off the text by holding run, so we can look at it hopefully a little more clearly. And let's plug this in. Let's attach our leads to positive and negative. All right, so I'm going to make sure my capacitor is discharged, and I swapped out this resistor for a 1000 ohm resistor instead of the last time where it was a 10,000 ohm resistor, just to make it a bit quicker. And if we plug this in, then hopefully we can count to 5 and essentially see it charge in that time. So I'm going to plug it in. 3, 2, 1, 2. Seems a little bit faster than the 5 seconds that I was expecting. So I'll discharge him and try it again. All right, let's plug this in again and try it. I guess it could be. Maybe what we can do is try a little bit higher resistance. So instead of using 1000 ohms and getting 2.5 seconds, we can use 10,000 ohms and get roughly 23 to 25 seconds. So let's try that out and see. So I'm going to make sure that my capacitor is discharged, and I'm going to plug out these resistors and add another 10K or 110K, which will just be attached right here. All right, so we have a 10,000 ohm resistor, and we're just gonna bridge the connection with our capacitor, and then I'll plug in power. So let's see if this is any clearer with these higher values, and we can run through the math and see how that checks out. But let's try this one more time. So I'm gonna plug in power here, and let's see if it takes roughly 20 to 25 seconds to fully charge. That's what our math is telling us. So in 3, 2, 1, I'll start the stopwatch. So he's charging. Definitely much slower with the 10K. We've gone on 5 seconds now. We're approaching 10 seconds. And it's hard to tell. Maybe the voltage is still going up. And it is. So before it looked like it was maxed out, but we can see that even though the line is at the top, the max voltage is still going up, just very slowly. And that's about 25 seconds there. And it seems to have reached a max. Might fluctuate, I guess, towards the top, but that was pretty on the money, I think. I'm going to discharge it and try it one more time. So that should be discharged right now. And let's try it one more time and see how this works. So I'm going to leave that on. I wish I could reset it. Don't know how to reset it. So let's plug this in again and see if we get our 25 seconds. So we're going 5 seconds right now. 10 seconds. And we can see our max has reset now to 3.3, so we're at 18 seconds. So it really does line up pretty perfectly to the 3.41, and we're at 23 seconds or so right now, and 25 seconds. So I'm pretty convinced. Very interesting how that works. So we know that this calculation, of course, works, or I should say I was able to get it to accurately do what it should be doing. So now what I want to do is just get some idea of what's happening. I know that the capacitor stops current from running, but what I want to do is maybe look at the resistor and see what's happening. So let me plug out power, because I know that the RC circuit is used for timing. That's what I've gathered so far anyway. So maybe what I want to try and do is use it for like a delay circuit. So we turn on a switch or something, and then there's a delay before the LED turns on instead of it being instant. In the last video, I was able to get the LED to kind of fade out, where the capacitor smooths out the power fluctuations if we had it, as a simulation. But now what I want to see is if we can use it as a delay mechanism, which is what it should be used for, I think. So in order to do that, what I want to do first is just get some readings of the values. We know that right now he should be charged to 3.42 volts. So let's just double check that. So we're at 3.32. I guess he's discharged a bit. So I'm going to discharge him. And it should be a very fast discharge. So there he goes, all the way down. And I'm going to plug in my power. And what I want to do is look at the resistor. So I'm going to plug him in. So right now he should be charging. And I want to look at what's happening with the resistor. We know it should take about 25 seconds to charge, which is plenty of time for me to get a reading here. And the voltage is dropping on the resistor. And this is kind of what I wanted to see. Because as the capacitor charges, I guess the voltage drop, or is it the current? I guess it all kind of works together. We can see the current dropping, right? I mean, we could look at the current individually if we wanted to with a multimeter, but we know that with Ohm's law, the resistance or the voltage divided by the resistance is the current. So in this case, we have a 1,000 ohm resistor right here, or a 10,000 ohm resistor, I'm sorry. And it's a pretty easy calculation. Right now it's at 0 volts, so there's 0 current. And it's just more reinforcement for myself to really understand that the current completely stops in the circuit when the capacitor charges. So the resistor just controls how fast he charges or discharges. In this case, we're at 3.41. We know it took about 25 seconds. So that means that to discharge, it should take just about 2 seconds. And we can kind of see that. I'm not going to time it or anything, but we can see that it's pretty rapid. So now what I want to do is try and use this to maybe, like I said, turn on an LED in a delayed fashion. We know that when he charges, he stops current. And I'm thinking that we can use that with a transistor to control what's happening on the base. So let's plug in our transistor here, just kind of in an arbitrary spot. And what I want to do is, we know that the transistor has 0.65 volt threshold on to turn on. So in other words, the base should be off until there's 0.65 volts. We know that the capacitor will reach that number after, a couple seconds using a 10K. So we'll actually need to look at something real quick. Apparently, we know that the capacitor is going to ultimately be 3.41 volts because we saw it on our oscilloscope. What T is actually, if I remember correctly, it's like 62.5%. So in other words, we saw that the charging, it goes up rapidly, but then it kind of like tapers off, right? And then it takes a long time to go up. So the initial T is roughly 62.5%. And I could double check that number, but I think I'm remembering it correctly from what I was reading. And Jay Beckva did say 2/3, which is 66%, 67%. So I think it's accurate. Maybe it's 63, I don't know. But the point is, if we get 62.5% of our 3.41, then we'll know how long it takes to reach that value. So hopefully we get lucky with our numbers here. Let's see. So 3.41 times 0.625 is 2.13 volts. So this is not very good for us. This means that our capacitor, well, we know this is going to take like 25 seconds roughly, plus minus. But for it to reach 2.13 volts, and I'll put here, it's 5T. So 2.13 volts is going to be 1T, or just T, right? Like one of these two. This is not division. And what does that mean? So 2.13 volts is in 1T. And in this case, what are we using? A 10K? We're using a 10K. So we have a 10,000 ohm resistor, and we have 0.6 well, 470 microfarads equals 0.470 millifarads equals 0.00047 farads. So we multiply these together. So we have 47 times 10, 0, 0, 0. So 1, 2, 3, 4. 1, 2, 3, 4. And we get 4.7 seconds. So that means that it's going to reach 2.13 in one of these, right? This is T. So if T is 4.7 seconds, then the capacitor, when plugged into a 10K resistor in series, it will reach 2.13 in 4.7 seconds. Now 2.13 is way higher than our 0.65 volts that we need on the base. So I guess it's going to be pretty immediate to turn on. So to have our delay, man, we need to really, how do I figure out how long it will take to reach a voltage? I guess that's the question. So we know that it will take 1 T to reach this value. And that's just because the rule is that it will 1 T's charging time goes to 62.5%. And then it very slowly, the rest of the 4 T's reaches 100%, right? If this is 100% charge or 3.41 volts, then if this is like a chart, then this would be 5T, this might be 4T, 3T, this might be 2T, and this is 1T. And this is time. So maybe if we just go really high over the number of the 10K that we're using, maybe that will work. So let's use like a 100,000 ohm resistor. So I think I have one around here, or it might be in a bag. So if we do this calculation again, but with 100,000, then we know, again, T equals R times C. If we're using 100,000 and we're at 470 microfarad, that's 0.47 millifarad, and that is 0.00047 farad. And then we multiply this by 100,000. So we have 0.00047 farad, and we move it 1, 2, 3, 4, 5 times. So 1, 2, 3, 4, 5. So we're at 47 seconds is our T. So we know that for our capacitor to reach 2.13 volts, which again is 62.5% of 3.41 volts, which is the max that we observed on the oscilloscope. This is in 1T that it takes to reach 62.5%. So our T is 47 seconds. So the capacitor should take 47 seconds to charge to 2.13 volts when we're using a 100K resistor. So let me get that. And hopefully, the whole point of this is hopefully to reach 0.65 volts, it will take some time to use as our delay. So let's get our breadboard back. It's 100K. So the idea again is that as a capacitor charges, when it's under 0.65 volts, the transistor should not turn on. So I'm going to move this transistor and let me plug out my power. And we're going to have this going from VCC, or our power input, to the capacitor, which will go into the base, I'm thinking, delaying when it turns on. Because if he wants 0.65 volts, then as he charges, when he's under 0.65, the base should not activate. So what we need to do is provide power for our collector. So I'm going to add power here that goes into the collector. And then we will just ground the emitter with the LED itself, I guess. So let's plug this in. Here was one line around. So here's how the circuit looks. Not sure if it will work. So it looks a bit confusing, but it's just the wires over each other. So this is a 100,000 ohm resistor. And all this is doing is powering the base. But we have a capacitor in the way. So the power goes through the 100K into the capacitor and then into the base. But the idea is that this guy charges, and he's very low voltage in the beginning. He's 0 volts, which should not allow the base to turn on because he needs 0.65 volts. So as he charges up, then the base should turn on at a certain point and turn on the LED. So I'm looking for a delayed LED turning on. So let's plug this in and see what happens. So I'm going to plug it in 3, 2, 1, bloop. And he turned on right away, which is not nice. Maybe I'm not understanding something. Or maybe he was charged. I think I discharged him. Let's make sure. So let's just double check. So I guess it doesn't matter which way I plug these in, really. But anyway, he's 0. So try this one more time. Let's put in our capacitor from our power to the base. And let's plug in our power. So 3, 2, 1, bloop. So he's turning on right away. That's so strange. I wonder what the voltage is on the capacitor, because it should be charging very, very slowly. Yeah, super slow. He's still at 0.2 volts, but somehow the base is on. I don't understand that. If I measure the base, and it says 2.44. So the base is actually... Oh, I think I don't know what's going on here. The base has more voltage than the capacitor, but it's connected to the capacitor. I'm not understanding something here. We can see how very slowly the capacitor is charging though. And by our calculation, it should take 47 seconds to reach 2.13 volts. Seems to me like it will take longer than that, but maybe I missed a 0. Oh, I think I did miss a 0. Maybe I don't know. I'm not really sure. Actually, I think I have oversimplified this. We do have other components now in the series, which must impact, I don't know, a bit over my head here. Still at 2.3 volts on the base. So this cannot really be used then in that case, for how I'm thinking. The base does not share the voltage. But we do know that in parallel, voltages are the same. So maybe let me plug this out. Let me discharge him. And maybe what I should be doing is connecting this guy to the base, but in parallel. Because I don't know who decides what the voltage is, but if he's deciding based on his charging, then perhaps that will work. Where they will share power. So in that case, we plug out my power. In that case, we should put our VCC directly into the base. And then the capacitor will be in parallel with the base. And I guess it goes to ground. In this case, I don't know. I mean, I don't know if this will work, but the idea is that in parallel, which these two are, the base and the capacitor are now in parallel to the resistor. So these two should share voltages. And what I'm thinking is that if he's charging very slowly, he starts at 0, then that would mean that the base also is 0. Unless, of course, the base kind of pulls this guy up to whatever the base is. But I think that violates his charging. So let's see what happens. I'm gonna plug this in. And we have nothing. Is it plugged into the right spot? I think it is. Let's check the voltage, I guess. So it is going up. Oh, look at that. The LED's turning on. So there is kind of a delay happening here. That is pretty interesting. But it's very slowly brightening. And that's not really what I want. I want it to just flick on after a certain amount of seconds. So maybe what I need to do is use another... Why wouldn't it just turn on? Like, once the base gets its value, shouldn't it just transfer from the collector? You know, one thing, funny enough, and coincidentally, that Jay Beckva was saying is that the current running through the base will allow some multiple, essentially, of current to go from the collector to the emitter. So in other words, it's not just a voltage that allows the floodgates to open and the collector to emit. Based on the current going to the base, that decides how much current goes from the collector to the base. So I guess I'm running into an issue where as the current rises on the base, the collector is basically able to or the emitter is basically able to sip current from the collector and gradually starts to flow until there's enough current to turn on and then illuminate really brightly. So let's see what's kind of happening here. Let's zoom out. So let's check the current on our base. We're at 2.45, and that should match what's happening on our capacitor, 2.45. So that does make sense. Any parallel paths share the same voltage, or are the same voltage. They don't share it. They're sharing current. So let's discharge this guy. LED stays on as it should, since there is power going to the base through this 100,000 resistor. And right now the voltage on the base is still 2.45. So if we plug this in, then that should mean current is now running through the capacitor, pulling the base's voltage down. So let's look at so that goes in, LED turns off as we expect. Let's measure this. So we're at 0.65 now. So the base should be activated at this time. We see that as it rises in tandem with the capacitor. I don't actually know when this LED is turning on. Last time it seemed to be about 2 point something volts, like 2.0 volts or 2.1 volts. But I'm not sure. I like that we've accomplished the task though, which is to delay the LED turning on, but the LED seems to be on now, very dim, and now it's starting to move up. And I guess I would suggest that the voltage on the LED needs to reach about 1.7 for it to turn on. So if we plug this out again, discharge, maybe looking at the LED will be the most illustrative thing. And we can kind of see in live action, I guess, the current coming off the collector, going into the emitter, and building up slowly. So let's put this in again. And let's take a look at this LED. So we can see the voltage is going up slowly. Does that match the voltage of the base? 0.81, 0.85. It seems to be slightly behind. Yeah, it's a little bit behind the base. So as this reaches about 1.7, it should turn on. Now, what I'm confused about again is well, actually, what I'm really confused about is he's getting current almost from the start. We see about 1.6 volts he turns on. Sorry to keep changing topics, but I'm just trying to stay on top of the readings. And then he'll just get really bright at 1.8. So very interesting what's happening. But what I'm confused about now is if the base is not at 0.65 volts, there shouldn't be any current coming from the collector to the emitter. So I don't see how the LED is gradually going up in voltage. Like right now, it's starting very low and going up, but the transistor should be off. So the transistor I'm not sure why that's happening. I probably just don't have a good understanding of really what's happening on the transistor, but it should be 0.65 volts before it turns on. Anyway, I think this is pretty cool. At least it illustrates that there is a delay on the transistor, which has a delay on the LED, and we see that when we plug it out. So let's discharge this one more time. We see that when we plug it in, it's pulling the voltage down on the base. I guess by having the current flowing from the resistor, it goes through the capacitor, the current, and then when we plug this out, of course, it turns on instantly because all that current is now running through the base. So I think I'll leave it here for now. I need to do some more research on these capacitors. I would like to make something that turns on right away after a certain amount of seconds. So similar to how this is very slowly turning on, what I want to do is have a transistor that once it reaches a threshold, the LED just turns on. So maybe I'll work on that for the next one.